Andrew is an associate scientist with CIMAS, affiliated with NOAA's Hurricane Research Division at AOML. His talk is titled HAFS Forecasts of Hurricane Melissa in Comparison with Aircraft Observations.
Thank you. Yeah, so I'm going to be talking about some of our modeling work, specifically looking at Hurricane Melissa. And the title is to ERC or not to ERC. So I'll explain what an ERC or eyewall replacement cycle is and maybe look at why it didn't happen in Melissa. So it's a short talk, so we don't want to spend too much time, but I do want to explain what an eyewall replacement cycle is. You know, if you've heard of a hurricane, the eyewall, that's the ring of strongest storms around the eye where the strongest winds, heaviest rain usually are. If you take a cross-section of a hurricane, you also have these outer eyewall or outer rain bands that can form. And so what can happen is over time, the outer eyewall basically chokes off the inner one and moves in, becomes a new eyewall. And this is a cycle that hurricanes go through. And when that happens, the storm temporarily weakens, and it can get larger. But it can, so these structure changes are important. And in Hurricane Melissa, it looked like there were a few times where this process was about to happen, because I was flying on the NOAA P3 and we were collecting the data in this, so we were following it as it moved toward Jamaica. And so you see these radar snapshots. You have this inner eye and then kind of this outer eye forming several times, but we never had a clear eyewall replacement cycle where this outer one completely took over and this inner one kind of just basically still stayed intact. And we saw the same thing on the radar, or the radar from the plane. You had these sort of outer bands or outer rings form, but they just sort of merged in with the other eyewall, and they never actually did a full eyewall replacement cycle. And so this is what, we looked at some of our HAFS, which stands for Hurricane Analysis and Forecast System. This is one of our models that we run operationally, now experimentally in NOAA. So this is the model, and then this is our aircraft observations. So two different configurations. This is one of our experimental ones. This is the operational one, so like what's run by the Hurricane Center in real time. Basically with kind of completely different forecasts, just a day and a half out of what the structure looked like. This one from the operational model looked pretty close to observations, but the experimental model here showed an eyewall replacement cycle actually happening. The one in reality was more like the merger ERC, which Michael has done a paper on, basically where you have the outer eyewall, rather than choking off the inner one, it just merges in with the previous eyewall, and the storm can stay stronger longer as a result. So we did some different configurations of HAFS using different model physics, different approximations for the convection, basically. And so we ran 3 different versions of this for that cycle, that initial time that I showed last slide. We did it about 2 days prior to landfall so that the tracks were good. So you can see all 3 of our versions were close to the observed track hitting southwest Jamaica. But notice we have very different intensity or wind speed evolutions with 2 of our versions, kind of intensifying close to reality, and one showing a big weakening and re-intensification. And this is when the version that was showing a full eyewall replacement cycle where you get that intensifying, weakening, and then re-intensification. So you have a big error here just as a result of having the wrong structure. So normally the output from this model is every 3 hours. We reran it in research mode, at 1 hour output to look at high density output of wind and the radius. Because the other thing is usually the size of the storm changes as a result of this process. And so we wanted to see what this looks like kind of in high frequency mode. And so this is what, from 2 of the runs, this is the one that kind of showed that, like what happened in reality where the outer eyewall just sort of merged in. You can see you have this single defined wind peak. You don't have this multiple peaks. Whereas in the other model run, you have this, at different heights, you have a clear double peak in wind with the sort of inner eyewall and then the outer one forming. And another way we can look at it is what's called a Hofmahler diagram, where it's time versus radius, and you can see a variable shading. And this is the tangential wind. So this is the speed of the winds basically circulating around the hurricane. And you see very different evolutions in the 3 different model runs. This is the one that I was showing previously, where it just sort of, the inner eyewall stayed intact and it merged in. This is where you get an actual replacement cycle. You see the big weakening of the inner eyewall and then the new one forming. What this is its vertical velocity, where, so the updrafts, that secondary circulation I showed before. So you can see, again, very different evolutions. You kind of have this inner eyewall. It's contracting as the storm initially intensifies, And then this outer eye wall forms, and you get this big area of sinking or subsidence between the two. This is called a moat, and this is something associated with those secondary eye walls or eye wall replacement cycles. So there's been some theory that has shown that what happens in the boundary layer and some of the processes there can be responsible for eye wall replacement cycles. So we looked at that secondary circulation. So where blue is inflow, red is outflow. This is radius and height up to about 3 kilometers in the storm. This is the radius of maximum wind. So this is kind of your initial eye wall location here. What you see is overall the structure is pretty similar. We had this inflow sort of outside the eye wall in all 3 cases. But what's different about this one on the right, which is the one that actually did the eye wall replacement cycle, is the inflow was maximized way outside the eye wall. So as the inflow brings in angular momentum from the outside and spins up the vortex, in this case it was happening at a much larger radius, and kind of the distance between those 2 eye walls was larger. And same thing for the vertical velocity. Again, remember this is that up part of the circulation. All 3 cases had sort of a double peak. You have your inner eye wall and your outer eye wall. But in these 2, which sort of just had the merger event that didn't actually weaken the storm, you see there's not much of that subsidence, not much of that sinking between the 2 eye walls, and they kind of just merge together over time. Whereas in this one, that inner one really contracted. The outer one was further out, so there's a bigger separation between the 2, and you got a lot of sinking air in between that chokes off the inner eye wall over time. And so kind of still is ongoing, but basically what this shows us is that the radial distance, so the distance between the inner and outer eye walls, seems to be key for distinguishing between the ERC and no ERC cases. So we get these outer bands that form, and it's sort of the distance between the 2 that's important. But it doesn't necessarily seem that there's a magical distance, so that's something we're still looking at. What exactly controls that? Because it seems like so far that the mechanism for how these different eye walls form seems similar. It doesn't seem like it's a magical difference in mechanism, but there's a lot of questions like, why does the inner eye contract more in that one run? Because that seemed to be key for getting that big separation between the 2 and that area of sinking. And so like I said, what controls that separation between the 2? That distance, if it's important, why is it 20 kilometers in one case versus 40 in others? And of course, this is just one case. This is Hurricane Melissa, but we've seen this in other cases. We flew another storm last year, Hurricane Gabrielle, that had kind of a quick merger like this. And so, this seems like it may happen more often than we realize. And so, how can we generalize this, and what can we learn to, better improve our models and forecasts going forward?